Good evening, everyone, and welcome to this, another one of our Charnwood Forest Geopark public talks. Some of them online, some of them in person, and thank you to everyone who's joining us tonight. Before we get started, I want to give a big thank you to the National Lottery Heritage Fund, who are supporting this and so much more of what Charnwood Forest Geopark is doing with its many partners across the Charnwood Forest area. If you have any questions tonight, rather than saving them up for the end, please do put them in the chat or the comments if you have an account on YouTube or Facebook. And if you haven't, you can email your question to jmatthews@nationalforest.org, or you can text it in and the number will keep scrolling across the bottom of the page while I'm talking. I'd recommend that you send your questions in as you think about them, because there is a slight delay between you sending them and me receiving them. So send them in as soon as you think. We'll collect those all together and we'll do some questions at the end. Now, we've had some fantastic talks already earlier in the year. We heard from a number of lecturers, Professor Benyon and others from University College London, who told us about the secrets of Groovy Pool mud. And then a few months after that, we were joined by Professor Carenza Lewis of the University of Lincoln, telling us about some of the important discoveries that can be found using the test pitting technique. And we heard a little bit about some of the discoveries that have been found that very week in Charnwood Forest. Now, we're hoping to bring Professor Lewis back to you a little later in the year when we've got more on those finds from Bow Manor Hall, and there'll be plenty more coming as we continue this series of talks roughly once every other month. But tonight, we don't have a guest speaker. You've got me. My name's Jack Matthews. I am the Geoheritage Officer for Charnwood Forest Geopark, and tonight I'm going to be giving you a beginner's guide to the geology of Charnwood Forest. So at that point, all looks like it's working well. So I shall bring my slides up onto the stage. And just a reminder, you can find more information about Charnwood Forest, the projects that we're working on, and the wonderful stories, both geology, biodiversity, cultural heritage, and other things at charnwoodforest.org. So let's get started on a beginner's guide to the geology of Charnwood Forest. Now, firstly, we've got to agree on what is Charnwood Forest. And here you can see our map of the 150 square kilometres of Charnwood Forest set in the beautiful countryside of Leicestershire. In the bottom right there, you can see the city of Leicester. In the top right, the town of Loughborough. And then coming down the western side, the left-hand side of the coloured-in area of Charnwood Forest, the historic coal mining communities of places like Thringston and Colville and others. Charnwood Forest is only around 8% of the county of Leicestershire, but within that is nearly half of the county's nationally designated natural sites. These are places like sites of special scientific interest and national nature reserves. You may have heard of those designations, those important designations for what they do for the protection of biodiversity, but many of them are also designated for protecting geodiversity, for protecting geology, fossils, rocks, minerals, and many, many other things. And we are almost uniquely blessed in Charnwood Forest to have such a rich area of both biodiversity and geodiversity, all within what is a relatively small area that one could drive across in about 20 minutes. So we're going to be going on a geological journey tonight, so it's worth putting things in perspective. Here is a very simple geological timeline of all of Earth history. The origin of the Earth on the left-hand side there from about 4,600 million years ago. That's 4.6 billion years ago. MA is the geological shorthand for millions of years ago. Now, on the right-hand side there, 0 MA, that's today. And 541 MA, 541 million years ago, is the boundary between the Precambrian and the Phanerozoic there in the light blue colour. Now, everything I'm going to talk about today is either in the blue part, the Phanerozoic, that's the most recent 12% of Earth history, or the very most right-hand pink section, the little sliver of pink right up against the blue section. So in relative terms, compared to the age of the Earth, we're going to be talking about things that all happened in the last 14 or 15% of Earth history, the last 600 million years. And yet we're going to be using terms like the oldest rocks in England, some of the oldest animals in the world. So that gives you an idea that even though we have some wonderful and incredibly old features in Charnwood Forest, the world itself is much, much older. And that's why there are so many other wonderful places to explore around the world that fill in the gaps, particularly of what is happening in that Precambrian era. Now, there is our geological map, much simplified on the left-hand side. Don't worry if you can't. In fact, you're not meant to be able to read anything on that map. You're just meant to be able to see that we are so blessed in Charnwood Forest to have, in a relatively small area, loads of different rock types. And we can tell on our map that we've got loads of different rock types because we've got loads of different colours. Geologists like to have a nice, colourful map. And we haven't got a boring one here in Charnwood Forest. We've got colours galore, more than 40 different rock types here in Charnwood Forest. And that's great because every rock tells a story. And with us having so many rocks, we've got many stories to tell. On the right-hand side there, that's a slightly more technical diagram. And again, I haven't put it big enough on purpose, so that you can't read the names, because the point is just to show how those layers of rocks are organized. Some of the colors correspond to those on the left-hand side, but you can see we've got lots of different rock types and they're all interacting with each other. Now, if you could read some of the words on that diagram, you would probably find, I'm sure we're joined tonight by people from all around the world. Do drop in the chat where you're joining us from today. And for those of you that are local to Charnwood Forest and Leicestershire, there are names in those rock units that you would recognise. Bradgate Formation, Beacon Hill Formation, Ives Head, Blackbrook, Shepshed, so many more, Maplewell, Charnwood Lodge. In fact, it is a testament to how significant the rocks are in Charnwood Forest that they ran out of place names. A good geologist names a newly discovered rock unit after the best place to see it. So it's usually a local place name. Now, sometimes that might be, rocks can exist over vast expanses of space. So, for example, I grew up in South Staffordshire on a house that was built on top of the Bromsgrove Formation, Bromsgrove being many, many, many miles away from South Staffordshire. The opposite is happening in Charnwood Forest, and a great example is in the area of Shepshed, in the south of Shepshed. I was talking just moments ago. There's a sandstone unit called the Shepshed Sandstone. And so what would happen when someone went and discovered a new unit of rock in Shepshed? They can't call it the Shepshed Formation. That's already been used. So it had to be called an even more geographically specific term, the Morley Lane Volcanics. There's about 6 people who live on Morley Lane, and they are, again, blessed by having their own rock type in southern Shepshed. So I just go into that to give you an idea of how unique the rocks of Charnwood Forest are, how many they are. And what we're going to do is we're going to go through a journey through time, starting with the oldest rocks and coming up to the modern day. I'm not going to talk about all 40, but we will cover the big important ones. And maybe if there's one that I've missed, you might like to ask me a question at the end. And just before we jump back in geological time, a big welcome. We've got people joining us from all over the Geopark and all over the world. Hello to Leslie. Hello to friends joining us in Thringston. Jenny, all the way in Bloomsburg, Pennsylvania. Welcome tonight. Lindsay's joining us from just outside Charnwood Forest in Ashby de la Zouch. And we're also joined by a friend from our sister Geopark in Newfoundland and Labrador. Alicia O'Leary joining us from the great province of Newfoundland and Labrador in Canada. You are all most welcome. Now we start our journey in the Precambrian, in that pink section of the geological timeline we talked about a few moments ago, but the most recent section of that pink on the right hand side. We're around about 580, 600 million years ago, and at this point the Earth looked very different. Now this is quite a technical diagram, so let me talk you through it. This is the arrangement of the continents during this time, around about 580 million years ago. But you've got to imagine that we're looking up at the bottom of the Earth. So right in the center of that diagram is the South Pole, and you're getting closer towards the equator as you go towards the outside. So we're only looking at a map of the bottom half of the Earth from 580 million years ago, as if we were looking directly up at it from the bottom. And you can see the important part we're interested in is the green section. That's a paleocontinent, an ancient continent that no longer exists in its own right, called Avalonia. And southern Britain, that is Wales and the southern part of England, as well as the Low Countries of continental Europe, is on the right-hand side of that green section. Our dear friends over in eastern Newfoundland in Canada, as well as Nova Scotia, are on the left-hand end of that green section. You can see a label called Gondwana. Gondwana is the combined continents of modern-day South America and also Africa, and you might be able to see the outlines there. On the western side, you can see Laurentia. That's most of North America, and you might be able to see the outline of Greenland in that as well. Also, Scotland is over in Laurentia at this time. So Britain, as we know it, hasn't been formed. Scotland is in a very different geographical position to Wales and England. Now, as you can see, fairly far south, Charnwood Forest roughly having a latitude of about 60 degrees south of the equator. That's a long way away from where we are today. And during this time, Charnwood Forest would have also looked very different than it does today. It would have been a chain of volcanic islands in what we call a volcanic island arc. So think of individual volcanoes making up islands, sticking up out of the sea, and then a deep ocean all around these volcanoes. So there's a little diagram of what this might have looked like. We're having occasional eruptions from these volcanoes and sediment being deposited out there and mixed in with the ash that is coming from those eruptions. Most of these Precambrian, or to be more specific, the name for that most recent part of the Precambrian is called the Ediacaran. That's the other word at the top of the page. Most of the rocks we have in Charnwood Forest from the Ediacaran are deposited in the sea around these volcanoes. So we don't actually have the evidence, the direct evidence of the volcanoes. You can't go somewhere and point at a rock and say, that was a volcano 580 million years ago. But we can see very, very clearly the evidence that we were quite close to those volcanoes, whether it be in the rocks of Bradgate Park and Beacon Hill, where those deep sea sediments, those silts and sands deposited at the bottom of the sea have minute amounts of volcanic ash mixed into them, or as we get closer to where those volcanoes would have been in places like Charnwood Lodge, a national nature reserve managed by our dear friends at the Leicestershire and Rutland Wildlife Trust. There you can see we're getting a bit closer to the volcano. We can see bits of volcanic material that have been flung out of the volcano and deposited. Still not the volcano itself, but it must be quite close if we're getting those bits of the volcano flung out. So this was the setting. This is the setting for the start of Charnwood Forest's story around about 580 to 600 million years ago. And the place to go and see this, the place to see the very oldest rocks in Charnwood Forest, is Morley Quarry in Shepshed. And there's more information about that if you'd like to visit on our website. Now, it was within these Ediacaran rocks in Charnwood Forest, those just slightly younger than I've just talked about, but still Ediacaran, around 560 million years ago, that a very, very important fossil was discovered. It was co-discovered by two school children in 1956 and 1957. Tina Negus and Roger Mason were their names, and it was very quickly published and recognized for its significance, because at that time, in the mid to late 1950s, everyone thought that the rocks of Charnwood Forest were too old to have fossils found in them. And as you can see on the left-hand side there is an image of the fossil, very clearly evidence of life. It is 21 centimeters long. The real specimen now is in the museum in Leicester, if you'd like to go and visit it and have a look. And it is a beautiful specimen of what we now call Charnia masoni. It was living on the deep sea floor all of those years ago, around about 560 million years ago. But it's taken a very long time to work out exactly what this creature was. Should also say, having been discovered in Charnwood Forest, it's since been discovered also in Australia, in Canada, in China, and in Russia. And that discovery in Charnwood Forest of complex life that was a little bit older than people were expecting led to many discoveries all around the world as well. So one of the things that's made it really difficult to work out what Charnia is or was when it was alive 560 million years ago is actually the lack of comparable features on it. On the left-hand side there, you can see a wonderful reconstruction of what Charnia might have looked like when it was living on the deep sea floor 560 million years ago, done by the fantastic paleoartist Martin Leicestr from Czechia. And as I was saying, one of the reasons why it's so hard to work out what these things are is it doesn't have the features that we would compare to in the modern day. So, for example, if I was roaming around in some Ordovician rocks, much younger than we're talking about here, and I found a new creature that was new to science, one of the first things I might do is count how many legs it's got, or what type of eyes it has. Does it have antennae? Does it have a shell? I'd look at all these features and I would compare things to the modern day, and I might say, well, it's got the same number of legs as an insect, and it's got some other features like an insect, therefore maybe it's a bit like an insect. That would be a very reasonable thing to do. But Charnia masoni, it has no legs, it has no eyes, has no hard parts, no bone or shell that we can see, no flowers or leaves or ears or a mouth, has no feathers or all the kinds of features we try to compare to. So what actually is it, and how do we know? Well, into the story comes the wonderful scientist, paleontologist, Dr. Frankie Dunn of the Oxford University Museum of Natural History. And she thought to look at the problem a little bit differently. She looked at specimens of Charnia from both Charnwood Forest, from Newfoundland and Labrador in Canada, and also from Russia. And she measured them and looked at the number of branches that they had. And she noticed that the baby Charnias, the little ones, as they grew by adding on new branches. So as they got older, new branches were added on. But at a certain point in a Charnia's life, it stops adding new branches, but it continues to grow. And that is to say that it gets to a certain point, which we might, for simple terms, though we don't know how long these things live for, maybe we just call it its teenage years, and it stops adding branches, and then it grows up into an adult simply by inflating the branches it already has. And Dr. Dunn and her team, combining this knowledge with some other observations of Charnia, were able to say that this is an animal. This is certainly an animal. And that means that also the forms that are related to Charnia must be animals as well. So she did a wonderful diagram of how it's related to other animals. I've simplified that for you here into a more cartoon form. So all of the animals, the metazoa, to use the scientific term, are in the light blue there, and they include at the kind of simplest end the porifera, which are the sponges. But within the metazoa, there is also the eumetazoa. Those are the more complex animals. And Frankie and her team showed that Charnia is not just a metazoan, it is also a eumetazoan. It's in the green block within there, and you should be able to see it. It's the first one on the left-hand side of the green block. To show you the relationships that were born out there, I'll point out some of the things. You've got the Cnidaria. They are the jellyfish and corals. You've got the Ambulacraria. They're things like starfish. The Spiralia includes mollusks and worms. The Ecdysozoa on the right-hand side, represented by that lovely ladybird, are the insects, the crabs and spiders, and we are part of the chordata, which I thought, rather than being represented by a human, as we are talking about Charnwood Forest, should be represented by a deer. These are things that have backbones, of course, so a deer is a wonderful example. So thanks to the work of Dr. Frankie Dunn and her team, we now know that Charnia is not just an animal, but more specifically, it is part of the eumetazoa. And that's wonderful, because then we can say that we have some of the oldest animal fossils ever described here in Charnwood Forest. A really important place to come if you want to understand the rise of animal life around 560 to 565 million years ago, and to understand the origins of animal life, the very first animals. But what would it all look like? So going back to Martin Leicestershire and his fantastic paleo art, he's made this wonderful reconstruction of what life would have looked like on that deep sea floor 560 million years ago in Charnwood Forest. So you should be able to see some Charnias sticking up there, some about 21 centimeters tall, some of them much larger. And on the left-hand side there, under the word ago, you can see one of these larger meter-long Charnias that are also found. On the far left-hand side, you should be able to see another frondose organism. That's Charnia discus. And then on the right-hand side, under the logo Charnwood Forest Geopark, you might be able to see a kind of stem with a goblet on the top, with this large holdfast disc on the bottom in light blue. That is Hylocalulis fordi. Thank you to Dr. Charlotte Kenchington of the University of Cambridge for naming that one. My dear colleagues in Precambrian paleontology, never pick an easy name for us to say. Now, just to the left of Hylocalulis is the purple-coloured. I should say, we haven't got a clue what they were actually coloured, so we've picked reasonable colours. We couldn't possibly know what colours they were in life, but just to the left of the blue Hylocalulis, you can see a purple Primo candelabrum, another example of a fossil first found in Charnwood Forest and also seen in Newfoundland in Canada. Right in the middle, you might be able to see a cabbage-looking form. That is Bragatia lymphadensis. described from Bradgate Park and its species name lymphadensis, named after the nearby village of Newtown, Linford. Also one of the oldest animals in the world. And then just sitting behind Bradgatia in the middle with its yellow tentacles is our newest fossil superstar, Aurora Lumina Attenborough. Aurora Lumina was discovered and written up, published by Dr. Frankie Dunn and her team. And this was an interesting one because it looks very different to all of the other fossils that I have talked about. All of the other ones have this kind of leaf or frond-like shape to them. And that leaf is subdivided into branches, and those branches subdivided into branches again. And so they look very similar, and you can tell that they are fairly closely related. The same is not true of Aurora Lumina there in the middle of the diagram with its yellow tentacles. It does not have the same branching pattern, and therefore it is not part of the group of related forms that includes Charnia and Primo Candelabrum and Bradgatia and others. If you've got tentacles, then you're clearly trying to grab something, and you're probably trying to grab those things for your dinner. Now, we don't really know what Aurora Lumina was trying to eat, but if you've got tentacles, and because of other features that Dr. Dunn and the team describe, science is quite confident that this is a cnidarian. So that's the group of organisms that includes jellyfish and corals and anemones and other things. So this is Aurora Lumina. This is the oldest predatory animal fossil ever discovered, no caveats or anything else, from Charnwood Forest. A fantastic fossil to have been found here, and a big part of our international claim to fame in Charnwood Forest, that not only have we got things like Charnia found in the mid to late 1950s, but things are still being discovered to this day. And that story was out in 2022 for Aurora Lumina and was covered on the BBC National News and I think the BBC World Service as well. So putting Charnwood Forest on the map. Now, it's not all about fossils in Charnwood Forest, though we're very proud to talk about them a lot. There were other things going on during the Precambrian, around about 560 million years ago. Here you can see a little cartoon diagram with one of our elusive volcanoes that we're not really sure exactly where they were. And this ash percolating down, mixing in with the sediments I've been talking about, and it's in those sediments that the fossils would have been found. But you could also have magma rising through the crust, but not making it to the surface to become a volcano. That magma can cool underground and become what we call an intrusive igneous rock. And this is exactly what's happened with the rock that you can see on the right-hand side there. That rock is a lump around about this big, if you can see my hands, and it is formerly known among geologists as the South Charnwood diorite, but we like to call it by its more informal name, Markfieldite. Markfieldite formed around about 560 million years ago as that magma, that molten rock, rose through the crust but cooled before it broke the surface, and it gives this wonderful speckledy coloured rock with dark greys and blacks, pinks and also greens. Very, very recognisable and found in a row, a kind of curving line of sites from Cliff Hill near Stanton-under-Baden, through Markfield, through Gruby and into the western side of Bradgate Park as well. And that little specimen on the right-hand side, the keen-eyed among you might have noted that the label in the bottom left corner is not just in English. And that is because this specimen is one of our rock ambassadors. And that specimen from Markfield is now on display in the Melodal Natur- und Geopark in Luxembourg, a UNESCO Global Geopark. and they have a display called the Wall of Geoparks, and we're very proud to be included in that and have Mark Fieldite there. So if you're ever in Luxembourg, do go to Melodal and have a look at their display, and you will see a little bit of Charnwood Forest on display, telling our wonderful story to the world. Now, we move forward in time to the Cambrian. The Cambrian being, in our diagram I showed at the start, the oldest part of that light blue section of the timeline. During this time, on the left-hand side there, you can see a kind of paleogeography, an ancient geography map of Britain during this time, or rather southern Britain, drawn by our dear friends at the British Geological Survey. You can see that most of southern England, Cornwall, Devon, and others would have been land at this time. Most of northern England would have been relatively deep seas or marine basin, as we have it there. But Charnwood Forest would have been right on the interface between land and a marine shelf. In geological terms, that means fairly shallow marine. And we have a number of deposits from the Cambrian, from a time more specifically in the Cambrian called the Comley series, roughly around 510 million years ago. The top picture on the right-hand side is a microscopic view of one of these units, a sandstone. This is the Stable Pit member, named after Stable Pit in Bradgate Park. This is sandstone deposited in shallow seas, and here that view of that image is only maybe about 10 millimeters wide, so you can see all the grains of sand there under the microscope, and we know that that must have been deposited in relatively shallow seas because we can see evidence for the sand being moved by tides when we look at it in Bradgate Park. So we've got the Stable Pit member, so much shallower seas than we were seeing previously in the Ediacaran with the fossils, where all of those deposits and all of the fossils within them were living in the deep sea, in the dark, deep sea. And that's, I should have said, that's one of the reasons why we know, even though they look like leaves, that they couldn't have possibly been plants, because they were living in the deep sea, and the deep sea is dark. And if you're living in the dark, you cannot be a plant because you need sunshine to survive. Now, the bottom right picture there, you might be saying, why has Jack put a picture of Johnson's Butchers and Deli in Woodhouse Eaves? As lovely as they are, the sausage rolls are wonderful and the coffee's great too. But why have I put a picture there? Well, it's a great representation of the Swidland slate, another one of our Cambrian rocks, quarried historically in Swidland Wood, now run by the Bradgate Park Trust, and also in other places such as in and around Groeby. And that is just a perfect example there above Johnson's of a Swidland slate roof. We're seeing greys, and if we could zoom in a bit more, you might be able to see some pinks and purples and green slates too. And a wonderful example, Swidland slate, being used across many of the towns and villages in Charnwood Forest. And we'll come back to the uses of Swidland slate a little bit later. But those are our main Cambrian aged rocks, so shallow seas during this time. Now we hop forward to another geological period, the Ordovician. We're about 450 million years ago. You can see on the left-hand side, the world has changed a bit since this time. We are that blob between the words Iapetus Ocean and Reik Ocean. You might be able to pick out the southern part of the island of Ireland and also England and Wales. There we are, part of that, Charnwood Forest, Avalonia, marching north. We're no longer 60 degrees south. We're getting closer to being around 45 degrees south at this time. The other part marked in red on the southeastern side of Laurentia, that is Scotland and Northern Ireland there. Those are Laurentian rocks, and again, still not joined together at this point. So that gives you an idea of geographically where Charnwood Forest was, around 45 degrees south of the equator. But what was going on in Charnwood Forest at this time? Well, we only have one Ordovician rock type, and that is from Mount Sorrel. On the right-hand side there, you can see a picture taken of Mount Sorrel Quarry. Mount Sorrel is one of the largest quarries in the UK, producing somewhere between 8 and 12% of the UK's entire crushed rock needs. A large amount is also exported and used for the by rail and use on the rail network. Mount Sorrel Quarry supplies around 50% of all of the UK's rail ballast needs. So if you are waiting at a station for a delayed train, have a look down at the ballast. See if you can see the wonderful pink rocks of the Mount Sorrel granodiorite. And you'll know that there's a little bit of Charnwood Forest nearby. Now, how did this rock form? Well, in a relatively similar way to the Markfieldite, a large, very, very large blob of magma rising through the crust, but cooling before it broke the surface. So this giant area of granodiorite, an igneous rock, a hard crystalline rock that we see around the village of Mount Sorrel, was formed deep underground by molten rock cooling and then becoming very, very hard. And obviously through time, that's then become exposed and has become a fantastic building resource that has been used for many, many hundreds of years. Now we skip forward to the Caledonian orogeny. Orogeny is a geological word that means a mountain building event, and it doesn't happen at a very specific phase. So I haven't put a date for this because the Caledonian orogeny lasts tens, if not hundreds, of millions of years. But what I have done there on the diagram on the left-hand side, again provided by our friends at the British Geological Survey, is show you in simple terms why we're having a mountain building event. You can finally see that Britain, right in the middle of there, the British Isles in bright red, have finally come together. And this is part of what happens during the Caledonian orogeny. Now, imagine great chunks of the crust of the earth, one with Scotland and Northern Ireland on, and the other with the southern part of the island of Ireland and also England and Wales, and you squash those together over tens of millions of years. It's like a drawn out car crash. And as things crash and are bumped into each other, they're going to get scrumpled up like the bonnets on a car if you are unfortunate enough to crash into something. And the same is true of the layers of the crust. And this is why the layers of our oldest rocks in Charnwood Forest are not flat and level like they were on the day that they were laid down, be it 560 million years ago in the Ediacaran, or more recent, or during the Cambrian 510 million years ago. Not flat layers at the bottom of the sea. Because of the Caledonian orogeny and all of this scrunching and bending and flexing, those layers have been bent up and folded. And that's what my diagram is showing there on the right hand side. All of this pressure and squishing and squashing has folded those layers. And this is why when you look at our oldest rocks, when you go to Bradgate Park, when you go to Beacon Hill, you are seeing these rocks slanted, tilted, because they are part of a huge fold that stretches all the way across Charnwood Forest. And that was caused as the building blocks of Britain were brought together, scrunched and almost welded together. And they've been the same ever since. But that's why our rocks, many of our rocks, are tilted. Right, we move on to the Permian. Around about 260 million years ago, during the end of the Permian. My little diagram there on the left-hand side is from slightly later, around about 240 to 250 million years. But you can see in roughest terms that Britain, the British Isles, and therefore Charnwood Forest, is somewhere near the equator and is at the centre of this humongous supercontinent known as Pangaea. It's a supercontinent because all of the bits of the continents of the world are not all spread out, they're all scrunched together. Now, of course, if you're near the equator, it's going to be quite hot. And if you're at near the centre of a giant supercontinent, it's probably going to be quite dry too, because clouds that form out at sea are going to rain out before they get to you. And because of this, we have a lot of wind-blown erosion during the Permian. We don't have any rocks from the Permian. There is nowhere in Charnwood Forest where I can point to a rock and say that is from the Permian period 260 million years ago. But what we can see is the evidence for those hot and windy environments eroding our landscape. So imagine all of the rocks that I've talked about and many, many more in Charnwood Forest from before the Permian. They're all sitting there in the middle of the land. They're not at the bottom of the sea anymore. They're in the land. And then all of those rocks are being sandblasted over thousands and millions of years by wind and all of the sand and the silt being carried by that. And it is therefore in this period, the Permian, 260 million years ago, that the topography, the shape of Charnwood Forest starts to be sculpted. Hills and valleys and hills that are made out of different kinds of rocks are sculpted in different ways. Those that are made of hard igneous rocks like the Markfieldite and the Mount Sorrel, they are sculpted into domed, like smooth, rounded forms. Those that are the Precambrian sedimentary rocks, those from the deep sea, they form jagged, tilting rocks similar to what we see today. And this all happened in the Permian. Now, the impact of that is that the topography, the landscape that we see today in Charnwood Forest is actually recycled from the Permian. Rocks have been deposited on top of it, as I will talk about in a moment, and they have been eroded away as well. But the essence, the foundation of our landscape was actually formed 260 million years ago during the Permian. If you see a valley in Charnwood Forest, that valley was first carved. It's been modified since, but it was first carved during the Permian. And if you are standing on one of our hills, that is a hill that was a hill 260 million years ago. Quite a fantastic feeling when you're next up on Barden Hill. Now, just after the Permian, we did get a few sediments deposited. This is the Triassic geological period. Just after the Permian, we're around about 230 to 240 million years ago, and we finally get a bit of water. Well, not just a bit of water, but sometimes a lot of water. It was still hot, it was still desert-like environment, and we've still got a lot of wind-blown sediment. But it's finally getting deposited. It's not just blowing off somewhere else. It is getting deposited, and it starts to fill in the valleys that were formed during the Permian. When it does rain, it was a kind of flash flood environment that could transport a lot of sediment, a lot of water, and sometimes some rather large boulders as well. And we see these in spectacular fashion in places like Barden Hill. There on the right-hand side is an image from the summit of Barden Hill, 278 metres above sea level, the highest point in Leicestershire, looking down into the quarry. And what you should be able to see is a V shape, a bit wonky on the right-hand side, but a V shape nonetheless. You are looking at a section through an ancient valley. The grey rocks at the bottom were carved 260 million years ago during the Permian to make that valley, and then that valley was filled in during the Triassic around 230 to 240 million years ago, filling up with sand and silt in that wonderful red sandstones that are very famous in the Triassic. You can find them. You can find Triassic sandstones all over the English Midlands, but you don't see a cross section of a fantastic valley filled in with the sediments anywhere better than Barden Hill at Charnwood Forest. And then we have many other examples in our quarries too. Now, we don't have Jurassic and we don't have Cretaceous. Who'd want them? They're full of boring dinosaurs. Our fossils are much more interesting than dinosaurs. We don't have lots of the geological periods that come after that. But what we do have is the most recent geological period, the Quaternary, the last 5 million years. The thin layer that sits on all of the other rocks is really important because it tells us about the glacial history of Britain and of Charnwood Forest, of glaciers and of retreat of glaciers and the flooding that happens and the rivers that come out of it. And it leaves behind a lot of pebbles. And on the left-hand side there, you can see a selection of pebbles that come from Charnwood Forest, grouped together in their classifications. Some of those pebbles come from rocks that are very known to us in Charnwood Forest. The top left there are some sections of Markfieldite, the South Charnwood diorite. On the top right-hand side there's some pebbles that were dumped by the glacier that were plucked from places probably like Beacon Hill and Bradgate Park. That line coming in from the left-hand side of kind of yellow ones getting smaller and smaller and smaller, that is flint, also known as chert. We don't have flinty or cherty rocks, so that must have been brought in from elsewhere. The 3 or 4 specimens halfway down on the right-hand side, that's limestone. It's an oolitic limestone. We don't have oolitic limestone in Charnwood Forest, so again, the glacier must have brought it in. And the big population of rounded pebbles at the bottom, they're called bunter pebbles, and they were all brought down by the glacier too. So our glacial story is important for our understanding of climate change, but also a fabulous opportunity to look at some rock types which aren't actually found in the bedrock of Charnwood Forest, but some specimens have been brought here over the past 5 million years via various glaciers and scattered amongst our fields. So another important part of our story. Now, do keep your questions coming in. I can see there's a few more, there's a few coming in already. And a reminder that if you can't add your questions to the chat or the comments, you can email me at jmatthews@nationalforest.org, or you can text your question to 07980 794 827. But to wrap up, I want to tell you a little bit more about the hidden treasures of Charnwood Forest, of our geology. We've zoomed through 600 million years. We've done Ediacaran and Cambrian and Ordovician, the Caledonian orogeny, the Permian, the Triassic, and also the Quaternary. But what has happened and what can be found in these rocks? Well, did you know Charnwood Forest actually has a fairly large history of earthquakes? Obviously not very big earthquakes, but the diagram on the right-hand side was published in the scientific journal none other than Nature. And it shows the scientists trying to work out the epicenter of a Leicestershire earthquake from August the 4th, 1893. Now, this is a very early example, this study, of citizen science. The scientists wanted to work out exactly where the epicenter was, so he put some advertisements in local papers, and people wrote back to him, and there were also stories written in the local newspapers. As you can imagine, hearing people's stories about earthquakes in England, they're not going to be full of destruction. They're a lot milder and somewhat more appropriately British somehow in the way that they're expressed. And here's a wonderful quote that in Hinckley during this 1893 earthquake, Miss Porter, engaged in dressmaking, saw the reels of cotton previously standing on her table dancing about, and a woman living up Mr. Porter's yard was so alarmed that she let her iron fall out of her hand. These are the tales of the impact of Charnwood Forest earthquakes, and using all of these data, it was shown that the epicenter of the August the 4th, 1893 earthquake was in the village of Woodhouse Eaves. Again, very, very small earthquake, but an important part of our story nonetheless. Oh, jumping around there, apologies. We have some fantastic mineral heritage here in Charnwood Forest. Many different types of minerals can be found. Most of them have been discovered in our quarries, and if it wasn't for the quarrying history of Charnwood Forest, we probably wouldn't know about all of these wonderful minerals that can be found here. They're very bright and wonderful. I've given you 4 examples there: azurite, palygorskite, malachite, and verzinite. And there are many more known from Charnwood Forest. But our most famous mineral from Charnwood Forest is bob kingite, because bob kingite was first described from Charnwood Forest. It could arguably say that having a mineral from Charnwood Forest is a rarer and therefore a bigger deal than actually having fossils like Charnia. And that is because there's only about 3,000 minerals that have ever been described and accepted by the international community. And here we have bob kingite. You can see the scale bar in the bottom right hand side there is 0.1 millimeters. It is an absolutely tiny specimen. It was obviously first described from Cliff Hill Quarry in Charnwood Forest, and it's since also been described from Spain and also from Greece. So a really important part of our geological heritage here in Charnwood Forest. And I should say it was named after Bob King, who was a geologist at the University of Leicester. Now, there is more than 2,000 years of quarrying heritage in Charnwood Forest. We know that because there are rocks from Charnwood Forest in some of the Roman buildings in Leicester. Some of the rock types, such as the Browgate Formation that I've shown on the top left-hand side of the images there, only really used in Charnwood Forest. Others have been used more broadly. So Swidland slate, commonly used for gravestones around the English East Midlands, and also for slate roofs, but they were used more broadly as well. There are several Swidland slate gravestones down in London, and the Swidland slate was also incorporated into the Albert Memorial, which is just outside Hyde Park in London as well. But our biggest geological exports in terms of building stones are the Markfieldite and the Mount Sorrel granodiorite, which can be found in sets, which are those cubes in the middle of the top there, used to make road surfaces, and also curbstones, most popularly used in the Victorian era. So if you're seeing Victorian curbstones and sets on a Victorian street, and you can see those speckledy green and pink and grey of the Markfieldite, or the pink of the Mount Sorrel, you know you're standing on a little bit of Charnwood Forest. And you can find those in Leicester and Nottingham, in Lincoln, Birmingham and Wolverhampton and Oxford and London, and many other places besides. And it's often been said that the streets of London are paved with Leicestershire, and it is because of those two rock types. Now, the rocks of Charnwood Forest continue, jumping around with the slides there again. The rocks of Charnwood Forest continue to be of great significance. We have 4 active quarries in the Geopark, and they continue to be of great use for large building projects. No longer are they used for sets and curbstones, more crushed stone, but if you're building a big infrastructure project and you need some jolly sturdy rock, then there's no better place to come in the UK than to Charnwood Forest. And therefore it's no surprise that such large projects as the Shard, the tallest building in the country, Silverstone, the new Wembley Stadium, the Olympic Park, the M25, parts of Heathrow Airport, the M1, they're all built on rocks from Charnwood Forest. So 2,000 years worth of quarrying heritage that continues into the modern day as well. At that point, we've gallivanted through more than 500 million years of Earth history, giving you the briefest overview of some of our most important geology and how our landscapes and our environments have changed over that time. If you'd like to find out more, there's lots of information on the website, charnwoodforest.org. You can also, on our website, sign up to our Geopark newsletter, which will keep you up to date on events like this and many others, and also how we're progressing on the various projects that we're working on. It's not all about geology, it's about celebrating. Our Geopark is about celebrating all of our heritage, and we have streams of work in volunteering, in the arts, in education, as well as protecting and celebrating our geology. And then on the right hand side there, I simply suggest that you might like to join the team, become a Geopark volunteer, whether it's helping out to look after some of our most important geological sites, or getting involved in creating learning resources, or helping us out at events. There are many ways that you can support the work of Charnwood Forest Geopark, and you can find out more about that and so much more at charnwoodforest.org. Right. At that point, I am going to turn to questions. I'm going to remind everyone that if you have any questions, please do write them in the chat or the comments. If you're unable to do that, please email me at jackmatthews@nationalforest.org or text me on the number that's coming across. I can see that there's lots of questions coming in, so give me a moment to sort through them. Right. Firstly, we've got a question. I should be able to make these pop up. There we go. We've got a question from Fudd, who asks, have any Charnwood fossils been tested for preserved cholesterols or sterols? Cholesterols and sterols, they're a type of fatty molecule. Now, some Ediacaran aged fossils that are slightly younger than the ones from Charnwood Forest have been tested from other sites in the world. But as far as I know, the rocks in Charnwood Forest aren't very good at preserving those kinds of molecules. We don't really have these organic molecules mixed in with the rock. Who knows, maybe someone can find someone, but I don't know of any experiments having been done for looking into preserved cholesterols or sterols, or indeed other fatty molecules in Charnia fossils or anything else. So maybe a bit of research for future, but my suggestion would be that the rocks of Charnwood Forest are not quite the best for preserving those, and perhaps our dear colleagues in Australia and Russia might be a little better, that their fossils are a little younger than ours. Good question though. A question from Andrew. Are these, I think he means the fossils, in deep or shallow seas? Yes, just a reminder that our fossils, Charnia, Masoni and all the others, were living in the deep, deep sea in the dark. They are deep marine organisms from around 560 million years ago. And I'm very glad to see that we are joined tonight by Martin Lysett, our wonderful paleo artist who did those reconstructions, who's joining us tonight from Kefalonia in Greece. Welcome to Martin. It's lovely to have you here. Now, our next question. A question from David, who asks, how was the boundary of the potential geopark originally agreed? Is it based on geological boundaries or other geographical or historical features? Great question, David. Obviously, that also gives me an opportunity to mention that, of course, we call ourselves Charnwood Forest Geopark at the moment. It is our aspiration in the next few years to move forward on an application to UNESCO for the area to become a UNESCO Global Geopark. And you can find out more about that on the website. Now, the boundary of the geopark is the same as the historic boundary of what's known as the Charnwood Forest Regional Park. A regional park is a non-statutory and non-legal designation, but an area with a coordinated set of management policies. And that was mainly brought together by the County Council and the other councils, Charnwood Borough, Hinckley and Bosworth, and also North West Leicestershire, all coming together with other organisations to work together for the common protection and conservation of Charnwood Forest. And it is that work that was part of the foundation of the application to the National Lottery Heritage Fund that funds the work that myself and my colleagues now work on. So that boundary has been set for around about 20 years, and we have adopted that. It's not simply based on the geology. It does make sure that it incorporates all of the Precambrian geology, which is of the greatest international significance to us, but it's also defined by a number of other things, including landscape character, and it went through a series of stages of public review and incorporated lots of charitable and conservation organisations' views into that. So there were many stages of consultation to set the boundary. A great question. Here's a question from Jason. Why don't we have Charnia alive today when we have representatives of other early animal groups? Why did Charnia go extinct? Thank you, Jason, for a wonderful, if difficult question. The answer is, I think the true answer is we're not really sure, but I might hazard a guess at why this is true. Can't really guarantee that I'm right, but I think it's reasonable to say that as we got towards the end of the Ediacaran, and towards the start of the Cambrian, around 540 million years ago, predators are starting to evolve. Animals that munch other animals are starting to evolve. And Charnia and these other things don't really have any defenses. They don't have any hard parts. They don't have a shell. They don't have bones, and they don't really have any other defenses. And some scientists have suggested that they were essentially munched out of existence. They were a branch of animal life that couldn't evolve or didn't evolve quick enough to escape the threat of predation as the more common predators that we see today, shrimps and crabs and things that look a bit like fish and what have you, all start evolving and go around munching things. That creates a kind of arms race, and perhaps Charnia and others didn't respond to that and just got munched out of existence. That's certainly one idea. It's not the only idea, but I think it's the most prominent one to mention here today. A great example, however, of how there are still many, many questions that need answering within Precambrian paleontology. And if we've got any young people joining us today, maybe you'll consider a future in Precambrian paleontology and geology and come and help us solve more of these questions so that we can have a better, more certain answer to Jason's very good question there. And I think we had a question on the text. Apologies, we'll zoom across to there. So we have a question from John. Do the Ediacaran Precambrian rocks surface anywhere else in the UK? John, a fantastic question. We also find Precambrian rocks, the rocks of sediments from the Precambrian in the Longmynd in Shropshire, and running up a little bit north of the Longmynd near Shrewsbury, though they don't have the complex fossils in that we find in Charnwood Forest. And there is also a chain of very small sites running from Church Stretton, Longmynd, down towards the kind of Tenby area, running through Wales. And at these sites, there are a number of fossiliferous sites. Most of those fossils are kept and on display in the Cardiff Museum. Things like discs and other things. So not quite as complex as the wonderful things that we're seeing in Charnwood Forest, but from around about the same time, some simpler fossils there as well. So yes, the story of Precambrian paleontology in the UK is more than just Charnwood Forest, but I don't think I will be annoying too many people if I say that in terms of Precambrian fossils, Charnwood Forest is the most significant site in the United Kingdom. And that is backed up by things like Bradgate Park being recently made a national nature reserve by Natural England because of the fossils that are found there. I'm just going to check if we got any other ones. Linked to that, we have a question From Fudd again, I have seen Ediacaran sites in Shropshire and Carmarthenshire. There we go. We were just talking about those. Is there an explanation of why only Aspidella holdfasts are found in Avalonian shallow water, but not Charnia? So let's just remind everyone what those things are that have been talked about there. Aspidella, these are the discs that are found sometimes. Sometimes in these age of rocks, we find discoidal structures, round structures, sometimes with lots of circles, all getting smaller towards the center, sometimes just with a central like boss. They look very much like the supporting structures, the holdfasts that stuck things like Charnia and Charnia discus to the sea floor. Not all Aspidella are found in shallow water. We do sometimes find them in shallow water, but they're not all shallow water. And certainly if we go to sites in Newfoundland, in eastern Canada, we can find Aspidella in shallow water. I have a feeling that we don't really know exactly what Aspidella is. Some people say they are all these holdfast structures for things like Charnia, but you're not preserving the frond above it. I think there's a lot more work to be done, and I think we need to do a lot more work on which are the shallow sections, which are the deep marine sections, and how are they related to each other. So essentially, I'm saying we don't really know. We haven't got a good enough answer, and I think our dear friends in Newfoundland will probably be part of the answer to that, as they have many, many more rocks to play with and look at and investigate. But thank you for that question. A fantastic question now coming in from David. How can we best protect the most significant geology from potential threats? While you will think about that, I'm going to have a drink. Well, it's important to note that there are many different techniques for looking after rocks, and it depends what the threats are, but also what the type of rock is, how it's going to erode. And certainly for Charnwood Forest, the rocks that we have we regard them as a non-renewable resource. That new rocks are not being exposed. It's different to rocks in a place like Dorset, the Jurassic Coast, where the erosion of the cliff is constantly revealing new fossils and new features. So if you lose a little thing, you might get another one come along. That's not happening in Charnwood Forest. What we've got is on a generational timescale, on the timescales of our lives, is all that we'll ever know. New material is new slabs of rock are not being uncovered. We just have to study and find new things on the slabs that are already there. So it's important that we have national level conservation. So we have that through sites like sites of special scientific interest and national nature reserves. And we're very lucky in Charnwood Forest that pretty much all of the designations that we need for the legal protection of our fossils are already there. And they don't just protect our fossils, they also protect important mineralogical sites, sites that are important for their landscape and how the glacial history has modified the area, and so many other sites as well. But often with our most important sites, we just have to leave them alone. We have to make sure that they are truly, truly protected, because if they are damaged, they will be gone. I personally am a great proponent of trying to leave features, geological features in situ, rather than removing them and putting them in museums. It might seem like the obvious answer is to chop up these things and put them into museums, but actually recent work by people like Dr. Emily Mitchell at the University of Cambridge has shown that we can reveal a lot about the ancient fossils of Charnwood Forest by studying them as communities, by looking at how they are spread out on the rock surface, how they were living next to each other or not next to each other. And she and her group are doing a lot of techniques on, nearest neighbor analysis, it's called, and other techniques. Now, if someone like me goes in and chops out a fossil because I think it's important and pops it in a museum, I have removed it from the community of fossils. And therefore, those kinds of studies that are revealing new things about these fossils can't be done. So we should try and leave them in situ. And actually, our biggest thing for protecting the fossils of Charnwood Forest is that we don't tell you where any of them are. We keep the localities secret, and if there is anyone watching here who does know where the fossils are, I would ask that you also join in keeping them secret. Unfortunately, there is an international black market in these fossils, and so it is upon us as professionals, but also as members of the local community, to look after these fossils and preserve what is our Charnwood Forest and Leicestershire's most important geological heritage. So thank you very much to David. I'm not seeing any other questions. So at that point, I am going to say thank you so much for joining us once more. If you have a friend who wanted to be here tonight but couldn't make it, well, that's fine, because this recording of this talk is going to be up on our YouTube channel. You'll also be able to watch it again via our Facebook channel, and you can share it with all your friends who want to also undertake a beginner's guide to the geology of Charnwood Forest. There will be more of these, whether they're about geology or ecology or other themes, archaeology, everything that makes Charnwood Forest so special. Every other month, there'll be something on, some in person, some online, always an opportunity to learn more about Charnwood Forest. So thank you finally, for the final time, for joining us here tonight. I hope you've had a wonderful time. You can contact us through the website if you have any further questions, but have a wonderful evening, and we'll see you next time when we have a Charnwood Forest public talk.